Hello, everyone, and welcome back to another episode of the series of Learning C along with me. Now, today's video, we're going to be taking a break from learning new concepts, and we're going to try to apply what we know into an actual useful program. And along with that, I'll be teaching you about binary search. Now, if you're watching this video and you're not following along the series, I do recommend that you start with that if you want to learn how to code in C. But if that's not what you're looking for and you're looking to learn binary search, then this works too. We're going to be focusing on binary search today. Now, what I have in front of me is this list, and this list, it contains numbers. And now, the only information I'll give you about this list is that it is actually sorted. And this means that the left-hand side is always it's always less than or equal to the right-hand side. Meaning that this value right here is the min, and this value right here is the max. Now, what is so important about binary search? Well, let me run you through a quick demo. Let's say I told you that I'm looking for the number 3. Okay, and I want to ask you, is it in the list that I gave you, or is it not? Now, the operations that you have is you are able to check you are able to flip any of these boxes, and you can check what number there is. And your first intuition might be to whoops, we don't want to erase the box. Your first intuition might be to just, well, flip each number and look for it. But we, of course, are programmers, and we don't look for the easy way. If we coded the easy way for everything, no program would really be that complex. We look for the efficient way. I want to find this 3 in the least amount of boxes opened. I don't want to open every single box to find it. Okay? And maybe I get lucky and I get it on my first try. That's not efficient enough. I want it so every single time I run this algorithm, I'm going to get a pretty good number of boxes turned. I want it to keep it as low as possible. Now, the important thing to remember is, well, it's sorted, right? Well, the most logical and reasonable thing to do here is to always check the middle one. And how do we check the middle? Well, we count. Obviously, there are 16. 1, 2, 3, 4, 5, 6, 7, 8. And that makes this the middle. So we're going to check it. We get 8. Okay, we didn't get the 3 we want. So what next? Well, remember, left is always less than or equal to the right. And if we have the 8 here and the 3 here, well, 8 is actually greater than or equal to the 3. What does this mean? It means that the 8 is on the right and the left is on the 3. We've all of a sudden narrowed it down to here. And what we can do is actually take these, just leave the rest of the list behind. We don't care about that anymore. And, well, wait a minute. We have the same problem again, except instead of 16 boxes, how many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. We've halved it. So we've went from 16 to 8. And here, well, you might ask, what now? Well, I still want the 3. Can I check every single box now? Well, no, because you're still going to be wasteful, and that's not how this algorithm works. What we're going to do is we're just going to repeat the process. Find the middle number, 4. Okay. Now, obviously, this 8 belongs here. We left it behind. Whoops, that's weird. Anyways, obviously, these numbers are in order. We could have just opened the third box right away. But we're gonna look at a scenario where maybe they aren't in order, and we can't just check the third box. That won't just guarantee us the answer. And well, anyways, from this 4, we can already tell that it's going to be to the left again. So we take this array. And well, we take this half. We don't need this one. And also, we didn't need this 8. So technically, it is only 7 boxes. But we'll just approximate it to 8. Just so we keep the numbers nice. We keep them to the powers of 2. And we'll see why when we look at the proof of this. Now we are at 4. We're just approximating to 4 instead of 3. Min, max. Check the middle. Oh, it's 2. Okay. Now, what do we have left? We take the 1 box that's left, split it up. This is both our min and our max, and because it's our only box, well, we open it, we check it, there it is, there's the 3. Now, if at any point the middle that we checked was the number we're looking for, we could actually end it right there. That's it, that's binary search. Now, sorry, this might seem confusing to you or a little bit more complicated. Why are we going through all of this when we could have searched every single box? And as a human being, you know what? Maybe searching every single one is more efficient. You don't have to worry about all the thinking steps. But this is a machine. This is a computer. You tell it what to do once, and every time you run the program again, it will know what to do, and it will do it very quickly. But when we do things very quickly, and we give it large amounts of data, well, we want to make sure that we're not wasting operations, is what we could say. We don't want to be flipping every single box if we don't want to. Now, again, I told you that this might work even if the numbers aren't in order. What if we have something like this? And I told you I want to search for 8. Now, we don't even have 8 boxes, 4, 5, 6, 7. So we can't just open the 8th, but this still works. We get the middle. So that means since it's 10 and 10 is greater than or equal to 8, it has to be in this 1, 3, 8. And of course, we're pretending to be the computer, so we can't just see it with our eyes and say it's there. Well, we checked 3, and the 3 is actually less than or greater than the 8. And because of that, we know that it's somewhere here. So we pull this and we check the 8, and we found our number. And from there, we can either return that, oh, it's true, it does exist in here, or we could also be keeping track of indices in our list. Now, we haven't talked about lists or arrays in C yet, so the exercise that we will be doing won't be using them. We'll be making a game that sees how many turns the computer takes to guess the number that you're thinking about. And obviously, it can't get it on first try, it can't just read your mind, but we can actually do the math and approximate how many number of attempts it will take. And how do we do that? Well, here, remember, we started with 16 in our first example, right? And then we broke it down to 8, and then to 4, and then to 2, and then to 1. And then from there, we found our target. This is what we call the worst case. Like, for example, if our number is actually 1, we would have continued to divide and continued to divide until we were left with our left one. And it's our worst case because, well, we have to use the most amount of operations possible. So when we do the math, we're always going to assume the worst case because we want to take into account the most possible time. And then if anything, if our program can do it in anything less, well, great. It's more efficient, but we don't want it to perform it in a time that we didn't take it into account. Now, so we start at 1 and we double it when we move up here, and then we double it, and then we double it, and then we double it. So we went 2 times 2 times 2 times 2. In other words, 2 to the 4. And that is equal to 16, right? Well, notice something else about this. Let's call n is equal to 16. And n is actually the number of items. Okay, so instead of 16, we go 2 to the 4 is equal to n. And by using a log base, now in computer science, whenever you see a log, we assume that it's always a base of 2 because of binary. And that's just what's most commonly used in computer science. It's the standard of this language. So we just say log. So if we take the log of both sides, log of 2 to the 4, and log of n, we can move the exponent down. We end up with log 2 of 2 is equal to log 2 of n. And these two cancel out, and you're left with 4 is equal to log of n. And what does the 4 mean here? Well, the 4 is actually how many times we had to divide up our array before we found the number in the worst case. This is what we call a divide and conquer algorithm, because what happened was, well, we took the array, we figured out which half it's in, split it, and now we treat it like it's the problem all over again, but with a smaller array. And we repeated and repeated and repeated till we divided up the array till we only had one possible answer. And because we were always using this property that left is less than or equal to right properly, well, we knew that we never got rid of the number. And if it did exist, then it has to be that last option. And if that last option is not the number that we're searching for, well, then it never existed in there to begin with. Now, what do we say about this log of n? Well, in computer science, we use a notation big O of log of n. And this is the big O time complexity. Time complexity. I'll just spell it like that. And what this means is that this is just an approximation for it's an upper bound, because remember, this is the worst case scenario that we're taking into account. So we never get a case that's worse than this. And what does log of n mean? What is this for? Well, we didn't just use 4 operations. In the program, we might have added numbers, subtracted numbers, changed variables. That's a lot of different operations. But we only looped through the algorithm 4 times. And that's what we really care about. The rest of them, well, operations vary from machine to machine anyways. Well, there's no way for us to approximate it. But this is a way for us to be able to visualize how the time complexity grows based on the size. Well, this is n right here, and this is, well, runtime, I guess, and this is log of n. And it's not like you can plug in an n and get exactly how much time you'll get, but you can see that for bigger and bigger and bigger numbers, well, log of n doesn't really grow that much, which means that binary search is very, very, very useful for big data types, because we can split the array every single time. We can go from 1,000 points in an array to 500 in one go, right? Now, in the exercise that we'll be doing, well, our computer will actually be able to find the number that we're thinking of in log of n operations, where n is, of course, the number of elements that we give it. And you know what? Let's code it up in C. Obviously, we will use the standard IO stdio.h header file. So we have access to print, and we will be using scan, which we have not covered in the C series so far. So I don't expect you to know what it does. It is a little bit complicated when you really look deep into it, but I'll give you a very simple explanation to it once we get there. Now, we will start with our main. From there, let's have a counter that starts at 0. Okay? And this counter keeps track of how many guesses the computer, attempts. And from there, remember we said we haven't talked about arrays yet. So what we will do is represent this list by some minimum and some maximum. Our array will just be somewhere in between them, right? And we will let the user decide that. Okay. And from there, we can have another integer called result. And we'll set it to 0 for now. And what result will do is it'll keep track of whether the computer has guessed it or not. And then from here, we will print, and we will ask for the minimum. And then we will use the scanf function. Now, how does this work? Well, we will put a %d, and then here a comma, and then this symbol that you haven't been exposed to yet, and then we will put the variable. And what this does is actually it'll take a decimal integer input and it'll send it to the maximum integer. Now this has to do with addresses and pointers. We will talk about that soon. Just know that this is like just asking for an input and assigning it to maximum. And sorry. From there, we also want to, first let's create a new line so it doesn't get messy. We want a max. And we will do the same thing with scanf. Scanf. We'll do a %d. And we will assign this to, you guys probably caught this mistake while watching this, but this should be maximum. This should be minimum. Okay, perfect. And now we will use a while statement. And normally, in binary search, you want to check if you want to continue looping until your left, which is your minimum number, has crossed over your right, pretending that left and right are indices in the array, because if they've crossed each other, then you've searched the whole thing and haven't found your number. But here, because we're not using indices or arrays or anything, we'll just continue to go until result does not equal 3. Now, what does that mean? Well, result at 3 means not found. And it'll make sense in a minute. And here, we will first have to guess the number, and the program will always just guess the number that's in the middle. And middle is of course minimum plus maximum divided by 2. And we don't have to worry about this returning a float, because an integer divided by an integer in C will always return an integer. It'll automatically round down for you. And here we will print this guessed number. Computer has guessed. Now %d, and we'll create a new line, and we will pass through this new middle. Okay, we will increment the counter because we've used up a guess. Remember using the ++ because we don't care about the old value of that. And here, guessed, we want to update it, right? We want to figure out, sorry, I don't know why I keep saying guessed. It's because in the program that I wrote before, I used guessed. We want to update this result to something new, right? We want to check if we've guessed it or not. And For that, we're going to use a new function. We're going to call it print menu. And this is just so we can compress our code. We're going to print different options for the user. 1 means guess is too large. New line. 2 means guess is too small. And 3, you guessed it. Okay, perfect. And from there, we have a new integer result. Well, if you remember scopes, this is not the same result as that one. We'll use scan to get the value of result from the user. We'll do this. And we will return the result. And this means that whatever value they put in ends up being the new value of result here. And all we have to do is just call print menu with no arguments. And then here, based on our new guessed, well, if result is equal to 3, and of course conditions have to be in brackets, so if result is equal to 3, well, what do we want to do? We want to end the program, but first, because remember, 3 means you have found it. Oh, no, okay. 3 means you have found it. And remember, we're continuing until it's while it's not found. So we are going to print number of tries %d, and we'll pass in the counter, and we will return right here. So we will end the int function, and the while statement, everything will just end. Now, if it doesn't end, if we get to this part of the code, that means that we didn't return. So the game hasn't ended. So we could check. If result is equal to, now remember, 1 means too large. And if the number is too large, that actually means that our number that we've thought of should be to the left, right? So what do? We have to update our maximum number to our middle minus 1. So the next time that we calculate everything, well, our maximum is actually shrunk. It's more to the left, so we have a smaller array. Now, if this is not the case, and our number is too small, that means that our number is actually in the right portion of the array, and that means we have to increase our minimum to this. And the reason we do -1 and +1 is because we've already checked if the middle is the right number or not, right? So we do this to skip it because we don't need to include it. And if, well, not if, but we'll just have a return 0 here just by convention. And that should be it for this code. This should be our little mini game. And just to show you guys that it works, I'm gonna be going. What numbers do I want to take? My maximum number is going to be. I plugged into my calculator, and first of all, let's compile. So GCC binary search binary search. And of course, there's no way of us writing code without getting errors. Let's see. Forgot this. Did we forget anything else? Let's just try compiling again, see if we get another error. And reported. And of course, we missed a semicolon, missed an F here, and missed another one here. I believe that's it. Let's try. Oh, of course, we still have a semicolon missing here. Now we should be good. Okay. So now if we call binary search. Now, on my calculator, I put 2 to the power of 6, and I got 64. Now we're going to have a minimum number of 1, and a maximum, actually, let's do 2 to the power of 8. Let's make it bigger, which is 256. And if you remember from our proof, 8 should be the most amount of guesses that this takes. It shouldn't take any more than 8. And let's say our number is actually 4. We should have probably thought about that before I guessed. But 4. Well, we'll tell it. Number is too large. 64, still bigger than 4. 32, still bigger. Still bigger. Still bigger. And we found it. 6, less than 8. That's okay. Now, let's do this again. But let's say our number is now 1. This is the very worst case, right? So, our number will always be too large until we get to 1. And it guessed it. 8. So that means that our proof is correct. 8 is the biggest number of tries that it will take, and we got that from log of n, which would be log of 256. Now let's play this game for real. Let's say my number is between 1 and 1 million, and my number will be 100,885. Let's see if it can get it. 500,000, too large. 250,000, too large. 125,000. Okay, we're getting close. Too large. 62, too small. 93, too small. 10,9,375. That is too large. Is it? Yes. Okay, 10,1, still too large. 9,7, nope, too small. 9,96, too small. 1,0,0,885 or 585. Ooh, we're very close. That is too large. Ooh, we're in the 8s. Too small. Now it's too large. Oh, we're very, very close. We are too large. We're too we're too small. Now we are too small. Too small. We're very, very close. Too large. Too small. Or not too small. You guessed it. We took 20 attempts. Now on your calculator, if you were to use log of 1 million, and this has to be log base of 2, you end up with 19.93, which rounds up to 20. And this actually ended up being a worst case scenario. And, well, that's everything for today's exercise. I apologize for the cough, but I hope you guys were able to put everything that you've learned so far into something, well, kind of useful, very fun too. Binary search is one of my favorite algorithms because it is a very, very simple concept, but you can do so much with it. Like, anytime that you are asked to search any array from now on, the first thing you should ask is if it's sorted. And if it is, then the first thing that should come to your mind is binary search because, well, it's the best there is. Well, thank you guys for watching, and I'll see you guys in another episode.